Hey everyone, so let's pick up where we left off from the last video where we're going to be doing an add to position method within our linked list. So the first thing we're going to do is we're going to try and draw it out to make sure we have a deeper understanding of what exactly is going to happen, and then we're going to go ahead and write this method. We're also going to consider a private helper method, node, get node, from a given position. So this will get us a node at a certain position. This will help us add to a given position. We're going to make this helper method just because in future questions, when we get there in a minute, we're going to actually need it. So perhaps we'll start without writing the method, and then we'll add it in later when we realize we're going to have duplicate code. We'll just sort of see what happens when we get there. So actually, rather than starting with code, I'm just going to grab my computer here. We're going to start with some drawing so that we can actually take a real look at what exactly is happening here. So let me just go ahead and share my drawing screen here. There we go. Okay. So we are talking about an add to position method. And add to position is going to take in an object that we want to add and the index at which we want to add it to. All right, so let's first talk about this in its easiest form. And in its easiest form, we want to add to the front of a list because we've already done that before, and that's when index is 0, right? So if our index is 0, add to front. That's easy enough to do. And now if our index is not 0, so if it's greater than 0, else we have to consider a few different things. First, we have to make sure index exists. Oh, for some reason my writing is questionable. Index exists. So this is when index is going to be strictly greater than 0, but it needs to be less than n. Is that right? It could be less than or equal to n. Because if it's equal to n, it goes in the last position, right? So if, just to make a note of what that meant, if our index is n, we're talking about the last position in the list. Yeah, that looks more correct. Okay, so we have to make sure that the index exists and that it's between these two positions, and this is how we get the last position. So there are 3 different cases of where we can add elements, right? We can add to the front. We take care of that case right here. We can add to the back. Adding to the back, we talk about it right there. We can add to the middle. And that's this one right here. And for what it's worth, these two can actually be handled together, and I'll show you how that's possible in just a minute. Let's start with our simplest case, though. Let's start with the case where we're adding to the front of our array list. I want to make sure I'm actually screen sharing. Okay, we're going to add to the front of our not array list, linked list. So there are 2 different scenarios when we're adding to the front of our linked list. The first scenario, so for front, the first scenario is that the list is currently empty. And the second scenario is if the list is not empty. Right? Straight and simple. Okay, so if the list is empty, that means that top is null. Right? That first element is going to be null. There's nothing in our list right now. If we're thinking about it like trains, top being the conductor is just standing outside looking at empty train tracks. There's nothing yet there. And this is a really easy case because if there's nothing there, we want to add something there. We just need to literally do that. Just new node into top. We're just going to create a new node and throw it into top and we'll be done. Now, if the list isn't empty, so if there are already some train cars there, like top is looking at a train car, and even if there's one or more, it doesn't matter what else is back here. All this doesn't matter. The point being, if there's at least one element in the list, it's simple enough. We're just going to make a new node right here where top is going to look there and new node is looking at the old top. Now, the neat key here is that in order to solve this problem here, we need to take our new node and point it wherever top is, just like before, and then make top equal to our new node. That's awesome. We've done this before. The cool thing is, of course, that this holds true for whether the list is empty or not. Because if the list is empty and we make our new node, and we make our new nodes next, look wherever top was, it's going to look at null, and then top can come here. So the exact same method, the exact same algorithmic steps apply in both cases with no issue at all, regardless if the list is empty or not. So if our index is 0, it's actually very, very simple. We're going to make a new node with the object data in it and the top element being next. If top is null, that's totally fine. That doesn't change this line of code at all. And then we can just say top is equal to new node. And we've added to the front of our linked list. I wish I would have written this in a different color because this is like actual code. This is first element. I just don't want to lose that code so we can actually build this out nicely. Okay, so that's all the first element. So now let's talk about if it's going to be not the first element. So there are two different situations that we actually care about, and they aren't add back, add middle, because like I said, we can actually do add back and add middle at the exact same time, for the same reason that adding to an empty list or not empty list at the front didn't matter. Adding directly to the back or into the middle will not make a difference for the adding portion for the exact same reasons. Because if we just treat null like any other node value, it won't be non-problematic for us. The two cases that we actually have to talk about when it comes down to adding to the middle or the back is the case where the index exists or the index doesn't exist. Now, the index not existing can mean two different things. One is that we're like adding to the end, and the other is that it would be like an index out of bounds. Right? Those are two different cases there that we have to consider. So let's start by drawing this out. Let's imagine for a second that we do have some data in here because we are talking about adding to the middle or to the end. So this looks something like this. And then there's some data in here. I don't know, we'll just put some integers in for right now. And let's say we want to add the value. Oops, I better just write it as a value to start. Object, what did I call it here? OBJ. Object OBJ is going to be like 4. And we'll say that the index that's coming in is going to be 2. Now, remember that these are going to be indexed in the exact same way that our array and array list are indexed. We just don't have random access. So this is spot 0, this is spot 1, this is spot 2. Okay, let's change this then for right now, just to make our lives a little bit easier for a minute, to 1. We want to put this into spot 1. Now, if you think about what happens in an array list when we add an element into an index position, everything from that position onwards gets like shifted over and the new thing gets slotted in at that spot. So if we wanted to do this right now, it would involve making a new node with the data inside of it. And we need to find a way to make this connection go here and this connection go here, right? We want to sever this connection and instead slot our new element in. So quite literally, you can think about it like train cars, where we're going to unlink the head of our train from the second train car. We're going to unlink them. We're going to move the new train car into place. We're going to relink the head to our train car, and we're going to relink our train car to what was before the second, now the third train car. We're literally just going to kind of try and shove it up into that position so that when this is all said and done, we end up with something like this. Hopefully in pictures, this looks like something that makes sense. Maybe you don't know how to get there at this point, but in pictures, we understand that what we want to do is take this box with a 4 in it and shove it into this position, and we can see how we can move the next connectors to accomplish this. So we can move this one's next connector to be attached over here to this entire object. And we're going to take this one's next connector right here, and we're going to link it over to this entire object. And then that way we can shove our our 4 value right in between those two nodes. So hopefully in theory, that looks like something that makes sense. Now, in order to do this appropriately, we have to be really careful that we don't lose any of our connections. We can't, as soon as we sever this connection, all of this is going to disappear unless we have some way to hold on to this node, right? That's super important here. So in order to accomplish this in an effective way, there's lots of different ways to do it. But in order to accomplish it right now, we're going to have some helpers. Just like when we were doing a traversal of our linked list in order to do printing, and we had a current variable, we're going to do something very similar here. We are going to keep track of our current node, which is the train car that we're kind of walking toward. And our current, if we write this down, our current node is actually going to represent, cur represents the index we are looking at or for. So that's the first thing that we're going to do is we're going to keep track of that. So when our current node is standing at the index we want, we have accomplished our goal, but we need one more helper to do this nicely. Now, there are ways to do it without one more helper, but we are doing it with 2 helpers. We're going to have a prev helper, and prev is going to represent the node behind cur. So I really like to think about this as if it was people in a train situation. I wish I had like a train picture here, but I don't. Maybe I'll go find one on the internet later. Top, we have 0, 1, 2, null, index 0, 1, 2. Okay, so now top is kind of like the person who's standing outside. I've been calling them a conductor, but maybe it would be better suited to just say like some kind of train yard director, because the top's job is just to say, I see the train. Imagine if trains would like, I don't know if anybody plays like Mario, but like when you see ghosts and when you turn away from the ghosts, they start to come at you. And then when you look at them again, they stop moving, right? Hopefully that is, I wish I was like in person. That's a thing that people like know what I'm talking about, like how the ghosts, like when you're not looking at the ghosts, they start to come at you, but if you're watching them, they don't move. You can kind of think about this like train yard helper in a similar way, where it's like as long as that train yard helper is looking at the front of the train stays put, it doesn't get collected by garbage collection. We can get to the whole train. But if that person like were to walk away, then we wouldn't be able to find the train anymore. It would disappear on us. So this person, their job is super important. This top person, they cannot move. If they move, the ghost, comes to eat you. The train disappears. We end up with a real problem. So in order to effectively move through our list, we need to enlist some helpers. We're like, hey, passenger 1, could you come help me? And so passenger 1 comes, that's going to be our cur. Passenger 1 is like, sure, I'd love to help you. And they come and they stand right here beside the conductor. Okay, that's our helper. And then in order to solve this problem even further, we are going to need one more helper, which is going to be our previous helper. And by default, the previous helper doesn't stand right beside top. The previous helper is just like over here hanging out in the yard, waiting for a job. They're like sipping on a drink, relaxing, waiting for a job, right? So they are technically null. They're just like hanging out in the sun, waiting for somebody to call them into work, whereas cur is already wearing their hat. They're ready for the job. They're standing right beside top. Now, the way that this works is both of these 2 people, cur and pre, both of these 2 nodes need to walk through the train looking for the index we're trying to find, which means we also need to keep some kind of a counter variable. So let's just pretend that Kerr is holding a piece of paper. I should start drawing these things bigger, where they're going to write down the train car number that they're on. So the very first thing that Kerr does is Kerr steps into the train. I don't want to. There we go. Haha, that's pretty awesome. Kerr steps right here into the train. I'm going to put it below it just to make my life a little bit easier right now. But there we go. Kerr steps into the train and says, like, check 1. I'm standing in the first train car. And remember, we are going to be looking for index 1. So I lied. This has a tally of, this piece of paper can't really keep that. It's got to keep the index. It's got to keep the train car index. So it starts at 0. And it's like, yep, I'm standing in index 0 right now. I am good. That's apologies. How odd that I receive a phone call, but it never actually showed up. My apologies. So we stand here in our index 0 train car, and Kerr is standing right in it, and previous is still waiting to be called in. So now, as long as we haven't fallen off of our train yet, and we aren't at the right position yet, Kerr is going to walk to the next train car. So Kerr goes and asks if I am still on the train or on the list, and my index is not yet found, walk forward. There we go. So Kerr goes ahead and walks forward. But before Kerr goes to walk forward, before that happens, Kerr has to say, hey, previous, could you come and help me out? So he, she, they calls Prev over to Kerr and then walks forward. So now previous has to get rid of their drink. They're no longer just chilling in the sun. Previous now comes over here and it says, hey Kerr, what's up? Kerr says, stand here. Hang out for a second. I'm gonna walk forward. I gotta move my if statement out of the way here. Puts that there. And then after we move to the next train car, the index sheet has to go up. Update index value. Okay, cool. So now we come back up to the top of this question. Sorry, I had to sneeze. We come back up to the top of this question, and now we ask ourselves, are we still on the train? Yes, we are. And is the index the same? Like, have we found our index? And now the answer is actually yes, right? Because the index we're looking for is 1, and Kerr is currently holding a 1. So now we're going to actually break out of our loop here, because clearly we had some kind of a loop going. We're going to break out and say, nobody move. We have all the things we need to make, to slide our new train car in. So then our new train car comes along right here and gets made. So new node created. And when this new node is created with 4, we have to somehow set something to next, right? Because don't forget, in our constructor, our node constructor takes in an object, and it takes in like an object value, and it takes in a node next. So what should next be? Well, if we look back up to the picture here, we can see that the next connector is supposed to be wherever Kerr is standing, which is super awesome. So that means this next comes right here. And when we create it, new node is created, we say new node, our data object that's coming in, and that next connector needs to just be equal to Kerr. And now this is going to be this next connector right here is going to be right there. You can imagine that there's a helper person here for new node. This is new node. And they're the one who's bringing in the new train car. So they're standing there and they're saying, hey, here's my new train car. Where should we link it up, right? And we're going to link it up to wherever Kerr is standing. So we can go ahead and do that. So now it's almost as if we have like an odd tree structure, because we have 0 and 4. both of which are connected to 1, which are connected to 2, which are connected to null. However, because of how code works right now, this says top. So if we left our method right now, this would disappear, garbage collection would come because that new node character walks away at the end of a method, right? Garbage collection comes and cleans them up. Nobody's going to be looking at this train car anymore. And like we said with the Mario ghost, if nobody's looking at it, it causes trouble, it'll disappear. So we haven't finished solving the problem yet. The next thing we have to do is we have to take this one's connector right here and connect it over here. Well, good thing previous is standing over there because previous can now head over to this link and connect it up to where new node is. So we can literally say previous.next, because that's our train car link. It's going to be equal to whatever new node is. Okay, now we've actually made all of these appropriate connections. And when the method ends, this person goes back to work. This person goes back to work. And by back to work, I mean like garbage collection, right? Because these were all locally scoped variables. They all go back to work. This connection was broken when previous changed its .next. And so now our conductor or whatever, our manager, our train yard manager, is looking at this piece of information right here, which is looking at this piece of information, which is looking at this piece, which is looking at this piece, which is looking at null. And we have successfully, without losing any of our train cars, none of them wandered off, sort of shoved another train car in there. We've shoved another node in there. So it's really important when doing linked lists that we have this opportunity to draw all this out so that we can make sure we don't lose any of those links as we're going through things. If we would have moved top, so if this person that's right here instead was the one to be the helper and they moved over here, let's say, all of a sudden nobody would be looking at this piece of information anymore. And so then this is going to be like, whoa, no one's looking at me, rah, and it's going to like run away. So it's really important that we bring in these helpers in order to solve our problems here. So let's get this in code, and then we will look at this situation of falling off of our list. Okay, let me share my desktop, make sure you can see things. Good. Okay, so in here, we're going to make, this is my main, a new linked list. And we're going to do add to position 0, add to position 0, add to, add to position 1, but we also, of course, have to pass in information. So we're going to pass in 0, 1, 2, and then we'll do exactly like our drawing. So list, add to position, and this needs to add a 4 into position 1, right? So up to like this is our what we drew. These ones are just going to be how we set it up. Let's actually just always add to front for a second because we know that we did add to front. So 2, 1, and 0. And then this is what we drew for a real add to position. The rest are just adding to front. So now let's go over to our code for that. Let's just zoom in a little. So I haven't written it yet. This is our like regular linked list class from the other day. I can just say public void add to position. We want to take in, we've been doing this, keeping it like capital O object so that it can sort of hold anything. And we're going to also take in the position. Now I've got my drawing in front of me of what I just wrote out. And so I am going to take the code that we wrote or pseudocode and put it in here. So if our index is 0, we are adding to front. And so if we're going to add to front, all we have to do is make a new node equal to new node, taking in the object, putting top here, and then we can say top equals new node, just as we did before. If we want to be really fancy about this, we can actually write it all in one line like this. Just a little bit more confusing to read this line, but basically make a new node pointing where top is, and then set top to that node. So it all just happens in one line, but the steps are technically the same. Now, if we want to add it somewhere else, we're saying that index is greater than 0. Now, if we want to be like very thorough, we should probably do something like if index is less than 0, we could like throw an exception. We could throw an index out of bounds exception, and we're like, negative numbers cannot be indexed. Right, so we can do something like that that allows us to just like throw an exception in the case where somebody tries to enter a negative number. Index out of bounds exception is a runtime exception, so I don't actually ever need to catch it. It will just crash the whole program, which in this case, I'm okay with. If I didn't want the whole program to crash when that happens, I would have to catch the exception and do something with it. But for right now, it's fine. I don't care. Let it crash. Somebody wants to try to add a negative number, let it crash because they are probably doing something wrong and the code should crash in this scenario. Typically, you don't want to catch runtime exceptions. Like you really don't. Runtime exceptions are because as a developer, you let something get far enough that something bad happened. So typically we don't want to catch those, but there's nothing wrong with throwing one. Okay, so now we have our index being greater than 0. And we're going to write that all of our code out. So we said we needed some helpers. First, we needed a helper cur, and cur was going to start at the same place that top was. And we also need a helper prev who's just chilling with a drink right now over in Nullville. Chilling with their drink, right? Having some iced tea, laying back in the train yard. Okay, and then what we want to do is we want to check to see while cur is not null, right? While they're still on the train. And we want to make sure that the index hasn't been found yet. And so in order to do that, we need some kind of an index counter. We'll say cur position, which is going to start at 0. And while cur position does not equal the index that came in, right? That's this one right here. Now, if this index is 0, of course, it comes in right here. So starting cur position at 0, we know that this is going to run at least once because this is going to say, if this is 0, this should not say 0 at this point in our code. Now, we can definitely make our code smarter in a little bit, but for right now, that makes a lot of sense. Now, what we want to do is we want to say, hey, previous, come hang out with me. Prev comes to hang out with me. Then I want to walk forward and say, hey, I'm going to go to the next train car. And then when I move to the next train car, I need to tick up my counter variable to say, okay, I've moved. And we're just going to keep doing that until either cur is null or the current position does not equal the index. And so right now, since we actually aren't taking care of this case, well, we hadn't in our pseudocode, what we wrote was, let's create a new node. Once we find the right spot, we're going to create a new node. And the new node is going to have the object data in it and have its next value point to current. And then we can have prev.next equal our new node. And again, we're not actually taking care of this scenario in this. Oh, yes, we are. Because the cur is null, meaning we fell off the list. While they don't equal each other. We'll have to try it. We haven't tried it yet. We'll have to try it. So then we're going to make our new node. We put object here. Cur is going to be here. And then previous.next is going to be here. Now, I guess this actually does work. The question is just, what do we want to do if they enter an index that's like way bigger than acceptable? Like if they enter an index, like if there's 3 elements already in the list and they enter the value 3, it can go into that 3rd spot with no issue at all, because that will be when cur is null. We just want to connect to the end of the train. But if there's 3 elements and they enter 10,000, do we want to tell them they're wrong, or do we just want to add it to the end of the train? So right now we just add it to the end of the train. We're going to run it to show that off, or we'll show off both scenarios here. So in order to accurately test our code, we should look at our different if statements, our different else statements, basically any active code block. So anywhere we put these brackets, and make sure that we run a test case that pushes us into that bracket set. So in order to get into this bracket set, I'm going to need to have an index less than 0. So let's head over here and let's do exactly that. List.add to position. Let's try to add like 5 to position -1, right? So this should throw the exception we wrote. Okay, so we have that. Next, let's go back and look. Okay, so the next scenario is this one where we want to add to the front and make sure that that goes in. Well, that's actually what we're doing for all these, index 0, index 0, index 0. So check add to front works with no elements, because that's the first time we're doing it. This one is going to be a check that add to front works with one element. We'll just say one or more elements, like 1 plus, because it's the same. And then this is also checked to make sure it works with 1 plus element, just because we wanted to have more than one. This one is checking the exception that we wrote. This one is going to be like checking, check add to middle. Now we have two more things that we want to check. If we have 1, 2, 3, 4 elements in our list, our indexes will be 0, 1, 2, 3. So we want to see what happens when we try to add something to position 4. Position 4 doesn't exist. It is the end of the list, right? That's right at the end. And we also want to see what happens if we try to add like a value to position 10 bazillion. This is way outside the available indices, right? Saying 4 just adds us to the end of the list because there's only 3 elements, or sorry, because there is 4 elements, so they're indexed 0, 1, 2, 3. So saying 4 should just put us at the end of the list, but saying 100,000 is obviously well outside the size of the list. Now, after we do some adding, we should probably print out our list. And I've already written my toString, so that's simple enough to do. I'm going to print it right here after I do my initial adds. This is going to make my code hopefully crash, and I won't be able to get past it. So I'll have to comment this line out in a bit. But once I add to the middle, I'm going to want to print it out. When I add to the end, and I want to see what happens in this scenario also. So let's go ahead and give this a quick run. There we go. So the first thing that happened was we added 2, then 1, then 0, and we added them all at index 0. So this should print out 0, 1, 2, which we can see it does do, which is fantastic. And that's this one. And then this one here says it should throw an exception that we wrote. And if we look, we are getting the exception we wrote, index out of bounds exception, which is the one that I threw. And we can see it's printing out my error message, negative numbers cannot be indexed. So that's awesome. We know that that works now, and we definitely have to comment it out if we want our code to keep running, since I am not doing a try catch. If I wanted to, I could, just for testing purposes, as loud as I can possibly say it, just for testing purposes, I can put this inside a try and put this in a catch of an index out of bounds exception, IOBE, and I can just say right here, IOBE.print stack trace and expected exception thrown here. So now when I run this, it will catch the exception. It will handle it like this, but my whole program won't exit. It'll just say, yeah, we caught what we expected and let's keep moving. So let's take a look at that. So here we can see first we had this, then we print out our stack trace. And then we said this was an expected exception. So that's awesome. And now our code can keep running. So next we try to add to where is it? The middle. So we're going to try to add a 4 into position 1, which is exactly what happened. 0, 1, 2. We moved right here into position 1, and then the other 2 things shoved over. We can see that when we added to the end of the list, our code was very happy to add right to the end of the list because this was position 0, 1, 2, 3. So position 4 was right here. And then right here we have 0, 1, 2, 3, 4, 5. But a reminder, this isn't in position 5 as far as our front end knows. Our front end was trying to add to position 100,000. So we have to decide if that's okay or not. And since this is pretty unexpected behavior for entering an index super far outside of what we expect, I think we should probably handle this case as an index out of bounds. This is okay. It's technically out of bounds, but because it's how we would add to the end of our list appropriately, it's a fine way to handle it. But this is not the end of our list. This is out in the middle of nowhere, and we should handle that scenario. And there's a really easy way to handle it. When we leave this while loop, if cur is null, it's because we're at the end of the list. So if cur is null, we must be at the end of the list. This can be done in one if statement, but I'm just separating it out for ease right now. If cur position is +1, cur position, if cur position equals the index that we're looking for, then it's the last element. So if at this point in time, the current position does not equal the index, index must be way bigger than the actual list. And in that case, we could also throw an index out of bounds exception, throw new index out of bounds exception, and we could make the message something like, this index is too big, period. There are only, and then we'll put the cur position, that many elements in the list. So let's go see what happens in this scenario now. So again, if we don't put this in a try catch, our code actually will crash at this moment in time. So instead of doing that, since what we're doing is testing our code, I will put it in a try catch. But again, in like submitted code, in actual development, in real production code, you wouldn't want to catch a runtime exception. So we're going to catch the same exception as before, index out of bounds exception. Whoops. And we're going to go ahead and do the exact same thing that we did before. We're going to say print the stack trace, and we're going to say expected exception. And then we are going to print it. We're going to print out our list to make sure that it actually didn't get added to our list. So let's go ahead and give this a quick run. We run our code right here. Make this a little bit bigger. Where did the run happen? Right here is where our run happened. So 0, 1, 2. Then we got our index out of bounds. That didn't change. Neither of those changed. This says 100,000 is too big. There's only 5 elements in the list, and it didn't add it. So we did a great job. I just want to draw your attention to the fact that right here, I didn't actually put this into an else. I didn't put this into an else, but our code also didn't add the element. Reason being, when you throw a new exception, if you don't remember, this is a reminder, we basically exit out of the method immediately. So what we can do here is we can take this and we can say like that. Now, this whole thing can be done with so this is like our add to position method. But what we're going to actually do is we are going to refactor our code a little bit to make it smarter, given that we're about to write a second method, a delete from position method. What we're going to do is we're going to make this code now run in a way where we only keep track of one node, sort of. Basically, everything that's happening in here, all of this can really be in a get method, like this can all happen inside a get method that will return previous, is effectively what it ends up returning. It returns previous, and then we can use the knowledge of previous to do all of the other work, because previous.next is cur. So we can actually update this code a little bit to be a little bit smarter, so that when we are about to write some more code, we're going to be able to use a method. And now that I'm saying it out loud, we're going to do that after we write the other method. I think it'll be a lot easier to actually see what code moves over if we do that. I'll just close this up out of the way so that we can't see any of the implementation details for a second. I'm just collapsing it. It's still there, just collapsing it so that when we move on in our code, it won't be in the way. Okay, let's head over. Oh, move that. Let's head over here. Okay. So let's just make a quick note of what we just did, because when we add into the middle of an array, we had to shift all of our elements over, right? We could randomly access the position, but we had to shift everything over. However, here we don't have to necessarily shift everything over. However, we do have to iterate through a certain number of elements to go find the right position. So in an array, we're looking at shift. If we want to find position I, we have to shift everything from position I all the way to the end of the array over one spot and potentially run out of memory and then copy everything over. And all of these things might have to happen for an array. Now, in a linked list, we don't have to do any of that. However, we do have to go from index 0 up to I element by element. So what we can see here is if we know we have to do a lot of adding to, let's say, the middle or end of our list, like closer to the end of a list, if it's a really long list, it might not make sense to be using a linked list. A shuffle might take less time. But if we know we're going to be doing lots of adding to the front of our list or within the front few elements of our list, then this makes way more sense than an array, because in an array, we have to shift tons of elements potentially. And in a linked list, we're only going to have to sort of iterate through a few, and no shifting is required. Okay, so the next thing that we're going to do is we're going to do the exact same sort of method, except now we're going to do a remove. So we go and we find the object we're looking for, and we want to remove it from our list. I'm going to make an executive decision here that this is actually going to be in a separate video, just to sort of have a little bit more peaceful chunks of information. So make sure you have a good, strong understanding of how we manage to sort of insert that node in between other nodes, just so that you can feel really comfortable and confident with moving through arrays, or pardon me, linked lists, and also how you sort of connect the references. And then once you feel really nice and confident with that, come over to the next video where we are going to pick up right here talking about this deletion method that we're going to do next. Thanks.